Hi, today let's have a look at this small instrument. This is an altitude alert indicator. There are two knobs here. On the right there is the setting of the altitude. Here there is an adjustment of the pressure. There is also a flag. On the rear there is a circular connector. We can see on the sticker the reference of that device. This thing was manufactured by Aztec Division. First, let's open this thing to see what is inside. Okay. Okay, so this thing is locked. It was working fine before. Okay, so let's start with the electromechanical side. Okay, so this is interesting. So we can see first that there are two control transformers, it seems. Okay, so this one is a differential resolver with the orange ring marking here. And we can see that there is a limited range. Okay, so this unit has stops. Okay, so a differential resolver is something identical to a transsolver. A transsolver is a synchro, but with two windings on the rotor. So this is something between a synchro and a resolver. And a differential resolver is something identical, except that the rotor and the stator are permuted. That is to say that the rotor has three windings, like the stator of a transsolver, and the stator has actually the two windings, 4 wires. So this permits to save one terminal on the rotor. The stops here indicate that the connections between the rotor and the external connections here are done using hairsprings and not brush contacts. The second one is different, probably because obviously this is a dual synchro system. So this should be compliant to the standard ARINC 565 for commercial airliners. There is normally a gear train here with a ratio of 27. So one should be the fine synchro, second one coarse synchro. Because this synchro has stops, this synchro is obviously the coarse synchro, because on the standard, one complete revolution is performed with 135,000 feet. But the standard limits to 50,000 feet. So therefore, the range of the rotor is less than 180 degrees. So this is why it is possible to use a synchro with stops. It is not the case with a fine synchro, which should be this one, because the fine synchro has actually 10 revolutions, okay, from minus 1,000 to 50,000 feet with 5,000 feet per revolution. So this one should be a classic transsolver, probably. Okay, so this one is also a differential resolver actually, but without stops, obviously. Okay, we can see effectively the difference of rotations of these two synchros, you can see. Okay, so we can estimate the variation for one revolution of this one, because there is a flat area here on the shaft. Okay, so I will try to orientate this thing horizontally. Okay, so we have 50,400 feet. Okay, so we are close to there. And effectively 45,300 feet. So there is effectively, okay, so there are effectively 5,000 feet per revolution. So this is a fine synchro. It is difficult to measure the variation of that synchro for the complete range. But this should be compliant to the standard anyway. Okay, so there is a gear train between these two synchros. Okay, and there is a differential here for the adjustment of the pressure. Okay, so the adjustment of the pressure permits to add an offset to the values here, to the altitude actually. Okay, so we can see that there is a spring, it seems here. So this permits to limit the backlash, probably. So we can see also that this knob has a push button function. We can see the micro switch here. Okay, so this thing is a solenoid for the flag. We have here 3 bulbs in parallel, so this is for the lighting, I guess. Well, you don't see, but there is a small electronic board here. Okay, on that board there is one transistor in TO39 and a few passive parts. Okay, so this is a very nice construction. I paid this indicator $10 from eBay USA, so not expensive at all. So this one was very cheap. Okay, and there are 2 electronic boards. So we can see a connector, so I think it should be possible to remove the board. Oh, this is the first board. So there are several transistors, several op-amps. And this is the second board. In plastic dip. And we have an IC MC661P. You can see here 2 medium power transistors, probably for the power supply. We can see several Zener diodes here, filtering caps. Okay, we can see 2 ceramic capacitors here. So I think we have across these 2 capacitors the secondary winding of the power supply transformer. Yeah, we can see several diodes here. Okay, so these diodes are the rectifiers for the power supplies. And there are also 3 medium power transistors here. Okay, we can see here the wiring of that unit. We can see the transformer which is loose. Actually the transformer was soldered on the bracket here, but there was something wrong with the transformer. Actually it was glued to this bracket, so with the vibrations and time, the transformer separated from the bracket. Okay, so this is a nice construction. You can see that the electromechanical side is beautiful as usual. I think it can be interesting to do the reverse engineering and to try to get it to work. We can see here the setup for the test of this alert indicator. I have connected two synchro transmitters. We can see on the right here, one is a coarse synchro, the second one on the right is a fine synchro. On the left there are two outputs, one here and the second one on the right. These three LEDs permit to show the three windows. They are connected to the comparators. Okay, so one here, second one here, and the third one, the output here. First, let's see the effect of the synchros to the windows. Okay, so this is a coarse synchro. So this one is very sensitive. Okay, so let's see the effect of the fine synchro. Okay, you can see first that the medium window is activated here. Then we have the fine window. After that, the fine window is disabled and the medium window. Okay, a typical behavior is something like that. Normally the output should be activated on these two areas here. Okay, so it is the case with this unit, except that when the altitude is above this limit here or below this one, we need to reset using an external signal or the push button. Okay, it is the case currently. Okay, I will increase the altitude. Okay, so you can see we are on that area here. You can see that one output is constant and the second one is actually a pulse. The pulse is generated using this comparator and this RC network here, which permits to activate momentarily this output here. So I think that this output permits to activate a small alarm during 1 second, a chime maybe. Here we are in the middle here, and the alarm is off. Okay, here we are on the second area here. Here we are above this limit and you can see that the alarm is still activated, but it is possible to reset the alarm using the push button or an external signal. Okay, so we can see that we have other activations of the windows here. But actually the coarse window is not activated, so this is why there is no activation of the output here. So normally we should have 5,000 feet between each activation of the windows, so we can verify the first one, for example. Okay, the altitude alert is here, so 14,200 feet. So normally the next activation should be 19,200 feet. Okay, so this is the case. that's all for this altitude alert indicator. Thank you for watching and see you next time for another video. Bye bye. This altitude alert indicator is compliant with the standard ERINC 565, which was defined in 1968. Okay, so for the altitude, the standard says that we need two synchros, one coarse synchro and one fine synchro. Okay, so this is the air data computer. Okay, so there is one synchro transmitter, which is the coarse. Okay, so the complete range is 135,000 feet. Okay, but the standard says that there is a limitation to 50,000 feet. Okay, so this corresponds to a complete revolution of the synchro. Okay, but the limit is 50,000 feet. Okay, actually between minus 1,000 feet and 50,000 feet. Okay, so actually the actual maximum deviation is 51,000 feet divided by 135,000 feet multiplied by 360 degrees, and this gives a variation of the angle of 136 degrees. Okay, so this is for the coarse synchro, and there is also a fine synchro transmitter. This is a fine synchro transmitter, and one revolution corresponds to 5,000 feet. Okay, so therefore in between there is a train gear like that. Okay, with a ratio of 27. Okay, so 27 times 5,000 feet gives 135,000 feet. Okay, so this is a dual synchro system. So for a given altitude, there will be a specific position of the coarse synchro and a specific position of the fine synchro. So when the coarse synchro rotates 136 degrees, there will be 10 complete revolutions of the fine synchro. Okay. Okay, so now let's see the altitude alert. So we have here the synchro transmitters of the ADC. Okay, so this is the ADC, compliant to that standard. So this is the coarse synchro. Okay, so this thing is connected to the altitude alert here. Red. Okay, so this is the alert device and this is the ADC. Okay, so there is the fine synchro also. Okay, so this will be connected to two control transformers. Okay, so inside the altitude alert there is also the same gear train here. Okay, so the yes, on that direction. So there is also the division by 27 here. Okay, so actually it is the other direction. Okay, so the larger gear is here. So when there is here a variation of 136 degrees, okay, so there will be here a variation of 10 times 360 degrees. Okay, and this is coarse synchro and this is a fine synchro. Okay, something like that. Okay, so we have here the rotors. So one rotor here and a second rotor here. Okay, so the goal is to have a null signal on both rotors. So if you have 0 on both rotors at the same time, therefore the position of the shaft here will be identical to the position of the shaft of the data computer. That means that the altitude here will be the same than the altitude to be measured. Okay, so here we have actually a zero detector. Okay, so actually there will be here the first electronic circuit which will give a window. So this, there will be here a window which is actually larger than 5,000 feet. Okay, and here there will be another window, another electronic circuit which will give a second window which will be very short, because here there will be a positive signal inside 100 feet. Okay, and at the end there will be, to simplify, an AND gate here with these two windows. Okay, and at the output there will be here a pulse. Actually it is not a pulse versus time, it is a pulse versus the angle, which will be 100 feet width. Okay, which will correspond, okay, to the altitude. Okay, so this pulse will be present when the position of the coarse synchro and the position of the fine synchro are correct. So you can see that there are several problems. So if the window here is larger than 5,000 feet, we can have at the output here two pulses corresponding to two different altitudes. Okay, but if the window is below 5,000 feet, we can miss the pulse here. So we can have either no detection at all, we can have two detections with two altitudes. So actually this window is a little bit above 5,000 feet, and there is a third window which is created by the fine synchro here. So there is another circuit which permits to have another window which is actually at high level during, if I remember correctly, 1,500 feet. Okay, and this third window is fed also to the gate here. Okay, so there will be actually a gate with 3 inputs. Okay, so in that case we will have here the positive signal, okay, when both synchros are exactly on the correct position. So this is the general functioning of this altitude alert indicator. Okay, so we have 3 windows which are generated by analog circuits, and we have here an AND gate, and at the end here there is a flip-flop actually. Okay, so there is a flip-flop which is connected to the output here. Okay, so the output here is fed to the output of the device, to the rear connector, and there is a set, and there is a reset, which is, so there is a reset line. The reset line can be activated either by a push button which is present on the instrument on the front, or also by a pulse which is available on the rear connector. Okay, so this is the connector, and here also it is a pin of the rear connector. Actually on that device there are 3 different outputs. It can be interesting now to see how the coarse window is generated. Okay, so I will explain you first what is the transolver and the difference between the synchro resolver and a transolver, which is something in between. So the classic synchro is something like that. So there is one stator, okay, with 3 windings, X, Y, and Z, and there is only one rotor. Okay, so the voltage present across the rotor depends on the amplitude of these 2 signals. Actually there are only 2 signals, because the third one is the difference between the 2 other signals. So this is the shaft here, and suppose that we have the angle theta on the shaft. So if we look at the voltage here, so this is something like that. Okay, and if we consider the amplitude, okay, so that will be something like that. Okay, so the phase is 0 here. Okay, the phase is 0, and here the phase is 180 degrees. Okay. Okay, so of course the position of the signal so depends on the equivalent angle of the synchro transmitter. So there is another angle here, phi, for example. So this is for phi equals 0. Okay, so if you have a different angle here, we will have something different. For example, something like that. Okay, so this is for phi above 0. This one is for 5 equals 0. Okay. So this is a simple synchro. Okay, so it is important to note that the zero crossing here depends on the position of the angle phi. So this is why this thing is used in a servo control. So if you want a servo control, so you just need to amplify this voltage in order to detect this zero position here, okay, and to feed the output voltage here to a motor, okay, and the motor will drive the control transformer here in order to have 0. Actually, there are two zeros, one here and the second one, but one zero will be stable. That means that when the voltage is here or here, the motor will rotate in order to have this 0 here. But the second one is not stable. Okay, it will be on the other direction here. Okay, so that means it will return to that 0 position. But the servo control can lock on the wrong position if the gain of the servo amplifier is not high enough. Okay, so this is the gain of the servo amplifier. Okay, so the gain should be high, but not too high, because if the gain of the servo control amplifier is too high, the servo control loop can be unstable. So generally, the gain is several hundred, 100 to 500 and something like that, it depends. But the gain should be high enough in order to avoid the second 0 position here, which can be stable. If the gain is not too high, it will be difficult for the servo amplifier to drive the motor with enough energy, okay, to escape from this position here. So it is important to have a high gain for the servo control amplifier. So this is a simple synchro. Okay, so now let's see something a little bit different, which is a transsolver. The transsolver is close to a synchro, except that we have two windings on the rotor. Okay, so the second winding is orthogonal to the first one. So that means that if we consider the same voltages than the previous synchro, so we have something like that on one winding, for example, winding 1 here. Okay, the second winding will be actually in quadrature with the first one, in quadrature relative to the angle of the shaft. This is the angle theta here. Okay, so this is the second. So when one voltage is maximum, the second one is minimum, so you have something like that. This is the voltage number 2. So this is something interesting. So this is something between a synchro and a resolver. A resolver has also two windings on the rotor, but we have also two windings on the stator. Okay, so transsolver provides the link between the synchro with the three phases here and a resolver with the two windings here. In a transsolver, this is the rotor and this is the stator. And there is something which is very close to a transsolver, which is actually a differential resolver. So there is a differential resolver. Okay, in a differential resolver, this is the stator and this is the rotor. because actually if we want two independent windings, if we have these two windings on the rotor, we need actually 4 contacts, okay, on the rotor, which is complicated using brush contacts, for example. It's easier for the manufacturing of the differential resolver to have the 4 signals on the stator and only 3 signals on the rotor. The connection between the rotor and the external terminals can be done using 2 different things. You can have brush contacts. Okay, so brush contacts, you have actually you have a cylinder like that. Okay, and you have some rings of copper here. Okay, golden plated generally. Okay, and you have here the contacts which are done like that. So you have one on each side. Okay, something like that. So this permits to have the link between the rotor and the external connections here. This is some kind of brush contacts. I forgot the exact term for that. And it is possible also to have hairspring contacts. So in that case, we have the rotor here. And the contacts are done using hairsprings like that. Okay, and you have the contact here. But in that case, the range is limited. It is the case of one transolver or differential resolver. It is a differential resolver which is on that instrument. You have seen that there is a sticker on the rear which is written that the range or the angular range is limited. So there is a limited range. The advantage is that you don't have these contacts which can be problematic in long term. It is more reliable to have hairsprings contact, but the drawback is that you have a limited angular range, okay, less than 1 turn. So this is a hairspring, which is not common. Okay, I have seen 1 or 2 times this kind of synchros. Generally, you have brush contacts. For the last part, you see how the coarse window is generated using the transolver. The transolver is here. It is connected to the coarse synchro of the air data computer here. We can see that the voltage on each winding is rectified, okay, and filtered using this capacitor. There is a leakage resistor here of 500K. On the second winding, there is an attenuation of this voltage. The ratio is 0.12 here. Okay, and these 2 DC voltages are fed to a comparator here. Okay, so I have called this voltage V1, second one V2. Okay, so the comparator is sensitive to the difference between these 2 voltages. So we can see here these 2 voltages. The first one here has a full amplitude. The value is 1. Okay, so this is a relative value, V1. And the second one in red corresponds to the voltage V2 here, with a relative amplitude of 0.12. Okay, so this voltage is in quadrature regarding the first voltage here. So this is the angle theta here, the shaft. Okay, so one complete revolution of that synchro corresponds to 135,000 feet. On the second graph here, there is a difference between the voltage V1 and V2. So this is V1 minus V2. So you can see that it has the same shape, but there is a shift on the negative side here. Okay, so at the output of this comparator, we will have a signal like this one here. Okay, the signal will be positive most of the position of theta, except during this angle here. Okay, so I called h, which is the equivalent variation of altitude. Okay, so we can calculate this variation of altitude h, which is actually the window, the coarse window. Okay, so we have V1 is the sine of theta here. Okay, so this is valid from 0 to 180 degrees here. Okay, so V2 is 0.12 cosine theta. This is this voltage in red. Okay, so the difference is 0 in order to calculate this variation of altitude h. Okay, so we found that this value depends on the tangent actually of this angle here. Okay, so after calculation we found that this value h is actually 5,160 feet. Okay, so this window is effectively larger than 5,000 feet. So this is a method used by this indicator in order to generate the coarse window. On that system, there is also a detection of the presence of a synchro transmitter connected to each synchro. So there are two diodes here, okay, which are connected to each signal. Okay, so this one and this one. This voltage is filtered and this voltage is fed to a JFET. So there is a leakage resistor here. The use of these two windings permits to have a DC voltage here of approximately minus 20 volts for all positions of the shaft here. Okay, so on the drain of the JFET there is actually a signal which is at 0 when the synchro transmitter is not connected here. So when a synchro transmitter is present, this JFET is off. So this permits to detect if a synchro transmitter is connected or not. The output here, there will be actually the window, and here actually it will be other polarity here. Okay, the signal will be at high level for approximately 5,000 okay, and 200 feet.